Hey, it's Mr. Saltano. This video is going to be on the ideal gas law. So I brought a guest, just temporarily because we haven't seen him in a while. Say hello, kitty. This is Macaroni. Okay, now I'll let you go. Carry on with you. Okay, so this is on the ideal gas law. The ideal gas law is a formula. This is the formula listed here. It's PV equals nRT. So that's what we're going to be using for this unit, is the formula for the ideal gas law. And so first of all, what do all these letters stand for? Well, you probably have an idea based on what we've done in gas laws before. So if you had to guess, what do you think the P stands for? The P stands for pressure. And in this case, we're going to say kPa as an example of our pressure units. What do we think the V stands for then? Well, the V is for volume. In this case, we'll say liters as an example. And then, skipping ahead a little bit, what do you think the T is? T is for temperature in Kelvin. So we always have to use the Kelvin for all the gas laws. So we've seen all these ones before, right? The new ones are the N and the R. So it makes sense then with the rest of this unit that N is for the number of moles. So however many moles the problem says, that would be your N number. And then this is the weird one, the R value. This is called the universal gas constant. And for our purposes, the R value is always going to be 8.314. Now look at those funky units on the R value. It's liters, kPa, moles, and Kelvin. The reason is because the R value is kind of special in that it's meant to cancel out the rest of the units. The R value is a constant, so first of all, it's always the same number. We're always going to be using the same number for our purposes, and it's a constant, meaning it's not going to change. So in the equation, your pressure can change, your volume can change, number of moles, temperature, but your constant doesn't change. That's why it's called a constant. And so for ours, we chose the constant that has liters because we wanted to cancel out our liters, kPa because we wanted to cancel out our kPa, moles because we wanted to cancel out our moles, and Kelvin because we wanted to cancel out our Kelvin. So this looks like it's actually math happening here, but these are actually the units having math applied to them. So our R value is 8.314 liters times kPa over moles times Kelvin. So this is just the units for this one number. This isn't a formula or anything like that. This is just a weird set of units that apply to this number. Just to give you an idea, though, there are many different R values, and here are just a few examples of them, of the universal gas constant. And which one you use for your problems depends on what your pressure units are in, for example, or your volume, or what your other units are in. So, for example, here is one that we would use if we were using liters, atmospheres, Kelvin, and moles. And here is one if we were using liters, millimeters, mercury, Kelvin, and moles. So it really depends. You want to use the R value that matches the types of units that are in your particular problem. Now for us, for our class, it's nice because we're just always going to be using this one. Because we're always going to be working in liters, kPa, Kelvin, and moles. So that's why we use this particular number. So this will not change. So in all the problems you have, this will be already provided for you because it's a constant. It's the one thing that won't change in the problem. Okay, so let's look at a real example then. So, and look, here we see our constant is already here. These are just our funky units that go with it. And so the problem says if 1 mole of a gas is at 101.3 kPa of pressure and 273 Kelvin, what volume will it occupy? Okay, so then we're going to go ahead. The key part about these kind of problems is identifying which number corresponds to which variable. And here's our formula again, by the way, PV equals nRT. So first we're going to find our pressure. In this case, that's 101.3 kPa. So we enter that in. What's our volume for this problem? Well, we don't know what the volume is, and so we're going to leave that a question mark for now. What is our N value? What does N stand for again? Well, N is the number of moles, and the problem says 1 mole, so we're going to put in 1 mole for that. R is again a constant, in this case 8.314. And our temperature, what's that going to be for this problem? 273 Kelvin. Okay, so now we just take those values and we just enter them into the equation. So we have our equation P times V equals N times R times T. Some people say PivNerd to help them remember. I like PV equals nRT, whatever works for you. So then we take our pressure, 101.3 kPa, times our volume, I'm going to leave that as a V because we don't know what that is yet, equals our 1 mole times our constant, 8.314, times our temperature, which is 273 Kelvin. So that's how we set up that part. So if we were to kind of bring this down a little bit, we would have 101.3 times V equals this number. So all I did on this side was I multiplied the right side altogether and got this value. Now what do we do to get V by itself to solve for this? Well, all we do is we take the number, divide by 101.3, that'll give us our value, and the volume is 22.4. So then we're going to go ahead and get rid of our question mark, put in 22.4 liters as our volume. That sounds awfully familiar, right? 22.4, where have I seen that? Oh, that's right. 1 mole of a gas at STP occupies 22.4 liters. Let's see. Well, in our problem, we're at 101.3 kPa. That's the standard pressure. And we're at 273 Kelvin. That's the standard temperature. So we're at STP. So we've just proven, using the ideal gas law, that this is the volume occupied by 1 mole of a gas under those conditions. So the gas law works, essentially. That's why we use it. Now, when do we actually use the ideal gas law? So it's actually used only when we're not at STP. And the reason is because if we're at STP, it's safe to assume that 1 mole will be 22.4 liters of space. We don't have to do any calculations for that. If we're not at STP, those are the special conditions where we have to apply the ideal gas law, which is just that PV equals nRT. So that's it for the ideal gas law. Thanks for watching. Remember, chemistry is everywhere.